Hello class, and welcome to section 9.5, which is about scientific notation. By the end of the lesson, you'll be able to write numbers in standard form and scientific notation, and be able to compare and order numbers in scientific notation. So the first thing, we want to understand the difference between the two formats that we can write numbers in. So standard form is a way to write number without using exponents. So that's, for example, if you were going to write out 1 million, you would write out 1, 0, 0, 0, 0, 0, 0. So that's writing out 1 million in standard form. Scientific notation is a way to write really large or really small numbers without having to do all of these zeros. So it's going to give us a way that we can write these numbers out using exponents. The format here is a times 10 to the nth power. The a value has to be between 1 and 10. So it could be, for example, it could be 1.34, or it could be 6.2, or it could be 8. It has to be a number between 1 and 10. It could be 1, it cannot be 10. So it cannot be a double-digit number. It is a single-digit number, and it may or may not have a decimal after it. And then the times 10, the reason we multiply by 10 is because 10 is what allows us to move the decimal. So think about if you have the number 2 and you multiply it by 10, then you get 20. If you multiply it by 10 and then 10 again, you would get 100. So multiplying or dividing by 10 is what allows you to move the decimal without changing that actual number. So that's why we're using powers of 10. And then our n value is going to be an integer. So that's a positive or negative number. So positive 1, negative 15, positive 24. Some number is going to be up top here for n. So if I was going to write this 1 million in scientific notation, I would write 1 times 10. And then we've got 6 places here. So it would be 1 times 10 to the 6th power. Now, how did we get there? In order to do this, we're first going to look at how we got from scientific notation into standard form. So we've got 4 times 10 to the 2nd power. Instead of solving 10 times 10 to the 2nd power and then multiplying by 4, we can take our 4, and since this is a positive exponent, we're going to move the decimal to the right. So right now with the 4, the decimal would be after the 4. This 2 tells us to move the decimal right 1, 2 spaces. All of these blank spaces now are filled in with zeros, so 4 times 10 to the 2nd power is the same as 400. If I come down here to the bottom one, I've got 14 times 10 to the negative 6th power. Now we've got a negative exponent, so that's going to move us to the left. So we're going to start with 14. My decimal point would be at the end, and then I need to go 6 places to the left. So 1, 2, 3, 4, 5, 6. Again, that decimal point is where it would end up. All of these spaces are going to get filled in with zeros. So I've got 0.0000 to fill in those 4 empty spaces, and then 1, 4. So 14 times 10 to the negative 6 is 0.00004, or excuse me, 0.000014. So that's how we go from scientific notation into standard form. Go ahead and try these two on your own. So we end up with 5, 6, 9, and then 10 zeros after that. And for our second one, we end up with 0.0000325. Now we're going to talk about how we can go from standard form into scientific notation. Our first job here is we need to figure out the a value. So we need to put a decimal somewhere into this number so that it is a single digit number. So my decimal would go right here. So my a value is going to be just 7 in this case. Then I'm going to have times 10 And then we would have to move it 1, 2, 3, 4, 5, 6 spaces to get back where it was. So this scientific notation is 7 times 10 to the 6th power. If I come down to this second one, again, I want to find a place where I can put the decimal so that it is a single-digit number. If I put it here, that gives me 827, so that doesn't work. If I put it here, that would give me 82.7, so that doesn't work. So I'm going to put it right here, which is going to give me 8.27, and then we're going to go times 10 to the, again, we need to figure out how far we move the decimal, so 1, 2, 3, 4, 5, 6, 7. So we move that to the left, so it's 8.27 times 10 to the negative 7th power. Go ahead and try these two on your own. First one, we get 1.824 times 10 to the 7th power, and the second one, we have 6.7 times 10 to the negative 5th power. All right, now that we know how to convert between the two formats, we're going to talk about how we can actually apply these. So, about 1 million fruit flies weighs 1.3 times 10 to the 2nd pounds. How much does one fruit fly weigh? Write your answer in scientific notation. So what we're saying is we've got 1 million of these things. So we've got 1 million little bugs all on a scale, and that scale then reads 1.3 times 10 to the 2nd pounds. So first, since we're using scientific notation, we want to get this 1 million, which is 1 million, and we want to make that scientific notation. So we've got 1 times 10 to the 6th power. Now, when we do this, our original weight value here was 1.3 times 10 to the 2nd power. In order to figure out the weight of one single fruit fly, we're going to divide this by all of the different flies we're counting together. So 1 times 10 to the 6th power. Now, when we have our numbers in front, we're going to follow normal division rules. So I got 1.3 divided by 1, which is going to give me 1.3. And then we're going to use our exponent rules from the first part of this chapter, and we're going to say when we divide, we subtract. So I'm going to end up with 10, and then 2 minus 6 gives me negative 4. So I've got 1.3 times 10 to the negative 4 pounds for one fruit fly. So we were able to do the division with the numbers and then subtract the exponents. If you were multiplying, you would multiply the front values and then add the exponents. Another example here, scientists estimate that there are over 3.5 times 10 to the 6th power ants per acre in the Amazon rainforest. If the Amazon rainforest covers 1 billion acres, find the total number of ants and write your answer in scientific notation. Go ahead and try this one on your own. So we've got our 1 billion, which is 1 times 10 to the 9th. We are now multiplying these, so 3.5 times 1 is 3.5. 6 plus 9 gives us 3.5 times 10 to the 15th power ants. The last thing we're going to look at is comparing and ordering numbers in scientific notation. Comparing is just when there's 2 of them. Ordering is when there is more than 2 of them. So our goal here is to order the time periods to show the table from oldest to youngest. So we want the biggest number to the smallest number. When you are doing this, your first thing that you should look at is the exponents. So I'm going to come over to my table and I'm going to say, okay, I'm looking at the exponents. I've got 8, 7, 8, 7, and 8. So obviously the 8s are the bigger than the 7, so this 7 is going to be last. Now, since we have 8, 8, and 8, that's when we start looking at the A values. So 2.08, 4.38, and 2.45. So the biggest number is 4.38, which means that our oldest geological period is going to be the Silurian period. So that's our oldest one because that was our biggest number. Then we've got the Triassic period because that is our next biggest A value for the group that have an exponent of 8. And then we've got our last one, which would be the Jurassic period. So that takes care of all of our values that have an exponent of 8. And then we come down to this last one, and that was our exponent of 7, so it was automatically the smallest. So our Tertiary period is the most recent period. So again, if you're ordering, your first job is to look at the exponents. Start with either the biggest or the smallest, depending on what the question is asking, and then use the A values as your second option. For this last question, about 1.372 times 10 to the 7th power square kilometers of Antarctica and about 1.834 times 10 to the 6th square kilometers of Greenland are covered by ice caps. Which landmass has a greater area covered by the ice? Go ahead and try this one on your own. Because 7 is greater than 6, all we have to do is look at the exponents and determine that Antarctica has a larger ice cap coverage. If you have any questions about this or anything else from the lesson, please feel free to reach out and let me know.